Hello everyone, welcome back to our channel. In today's tutorial, we are going to build a complete semantic search engine that understands the meaning of your query and generates the search results. You'll see this kind of application in many real-world products like Amazon product search or YouTube video recommendations, LinkedIn job matching, etc. Where whenever users type questions in their natural language like show me budget friendly gadgets or jobs that allow remote work, etc. The system has to understand the intent and respond naturally and meaningfully, not just by matching the exact keywords. So before we start coding, let's quickly understand what semantic search actually means and why it's useful. In regular keyword based search, if you type something like affordable kitchen items, the system will only return results containing these exact words. Even if the product says budget cooking tools, it won't show up, even though they both mean the same thing. Semantic search fixes that by converting all the text, your existing dataset, and your query itself into vectors using a pre-trained language model. Then it compares these two, the dataset with your query using similarity search. This way, even if the words are different, you will still get relevant match if the meaning is similar. In this project, we will take a real world Kaggle dataset, this one, and generate sequence embeddings using a HuggingFace model and use FAISS to build a fast and efficient semantic search engine. Then after we develop all components for this semantic product search, we will develop a Streamlit app like this where the users can type their natural queries and get meaningful search results here actually. In phase 4 of this project, we will go one step further. In phase 4 of this project, we will go one step further. We will send all the retrieved results to OpenAI API and ask it to generate more meaningful and accurate results. Except this, everything else like indexing, retrieval, UI generation, everything we developed in local. So you can reproduce it and develop your own projects for some other purposes. We tried our best to keep the code clean and modular. So you can extend it to other domains like resumes, research papers, or creating internal knowledge bases, etc. Let's get started. Let's take our main product. Once the user enters a search query, like here we typed affordable running shoes for men with good grip, the app returns the results in three separate sections. This is section 1, we call it phase 3 basic semantic search, and this is section 2 called phase 3.5 filtered plus a sorted search, and this is section 3, it is phase 4 LLM grounded recommendation. We will go through all these phases in a while. Once the user enters a search query, like here we typed affordable running shoes for men with good grip, and here I am giving how many number of results that you want to see. So here I am mentioning it as 10. After we give these two inputs and click this search button, the app returns the results in three different sections. This is section 1, section 2, and this is section 3. Let's quickly walk through what each phase means and how it differs from the others. The first is phase 3. This is the raw output of our FAISS based semantic search engine. We take all product descriptions, embedded them using a HuggingFace model and sorted them in a FAISS index. The moment the user enters a query, we embed that query to and retrieve the top matches based on pure vector similarity, no filtering, no sorting, just direct semantic proximity. That's it. That's why you might see some duplicate entries or items that does not match all constraints like price, category, because this phase only cares about meaning and similarity. For example, here we used affordable, but here the products that we obtain are not sorted at all. So at least it would be good if we can get these results in a sorted way, means sorted with respect to price. In phase 3.5, we apply additional logic on top of this phase 3 results. So here we filter out irrelevant or noisy entries, applied price based constraints, and optionally sort the results. For example, if the user says affordable, like we typed in our query, we interpret them as the products under some 1000 to 3000 depending upon our logic, and remove anything above that. You can think of this phase as a production grade retrieval layer where we fine tune the basic semantic results to better match user expectations. And next, this is phase 4. This is LLM based recommendation system. So this is where we bring in the GPT. Here we take the filtered results from 3.5 and pass them through the LLM layer along with the original query and ask it to return a curated shortlist actually. Now the LLM does not generate new products. It selects from the ones that we already retrieved in the above phase, but it picks the most relevant ones, rewrites their titles if needed, and returns a cleaner list. So while this section might look similar to the previous ones, the ranking and phrasing here are driven by the language model reasoning, not just vector distances or filters. This is especially useful when you want to give the user a chatbot like or assistant like response, but still grounded in your actual product catalog. So this is the overall product overview. So let's dive into the actual code that drives this product. So this is the overall product. So here we divided this entire project into 5 phases actually. In phase 1, we will just clean up the data set, and then in phase 2 we embed the developed data set into a FAISS index, and in phase 3 we develop the basic semantic retrieval search engine and also the advanced search engine that we just discussed in phase 3.5, where we add some additional logic to sort or to remove duplicates, etc. We will apply some logic, and we will develop a filtered search engine in phase 3.5. Both phase 3 and phase 3.5 are covered in this phase 3 only. And in phase 4, we work on the LLM part of this project. And in phase 5, we develop a search engine product like this using Streamlit app actually. So here I have given some brief descriptions about how the keyword search works and how the semantic search works, and I have given some detailed understanding about this product. So if you have time, so please go through this notebook so you will get more idea about semantic search process actually. Let's first take a look at the our main data set. So this is where I have downloaded our data set. So you can also download this data set and keep it in your local. That's what I did. I just downloaded it and kept it in my local. If you look at the data, so when I download it, I get this archive directory. So if you open it, any file in this, so the basic file looks like this actually. It has these columns. So this is the name, this is the main category, and this is a subcategory, image, link, rating, number of ratings, discounted price, actual price, etc. These are the details that you have in this file. And similarly, if you go to other file, for example this electronics, you'll get similar list, okay, but you'll find some other examples data set where that doesn't have any data actually. This have some data. For example, this one, it doesn't have any data. So like that, you will have some spreadsheets that doesn't have any data. So if you look at here, if you go to top, these are all the files that doesn't have any data actually. So you just have to exclude this in your final data set. So what we are going to do is we just load each of this file and read into your local and do some filtering on this data, and then we will create a unified data set that has all of these products like this actually. So here I'm just loading some libraries, pandas and RE and some pathlib library to manage the paths. So here I'm just creating the data and I'm listing out all the CSV files, and overall we have 140 CSV files, and here I'm creating this load and standardize function. So what does we do is, so here if you look at here any file, so we have these things, right? Name, main categories, subcategory, image, link, ratings, number of ratings, discounted price, actual price actually. So of these products, so we don't need all these products for our search engine actually. So what we basically need are, so a title, product description, price, category, and the product link. These are the main categories that we are expected in. So for example, if you look at the data set, we have the name, okay, it is very long. Maybe we can split it and derive the description also from this. directly, and we just extract the price, category, and link from the website. So we will just retrieve all these columns from each CSV file and store it into a main product set. Actually, that's what we are doing here. We just load each of these files. So just I said, we have these file categories, right? Name, main category, subcategory, image, link, ratings, etc. And then what we do is we just extract the title, build a description by combining useful tools like ratings, number of ratings. We will just build the description in the way that we want actually, and then we will generate a final product list like this. Okay, so here we have a title, description, price, category, and link. So if you click this link, the links may not work now because this data set was somewhere created around 2023. So some of these links are not working. Some may work. I have not tried, but if you have some time, please try it and let us know. Okay. Once we have it, and then we will build a final data set combining all these things. We develop the final actually. So this is our final data set. It has around 1103197 rows, meaning we combined all the products in all the 140 CSV files, of which few are empty, right? So we just deleted them, and then whatever the products that are listed in those CSV files, we collected all those things and we developed this final product CSV list actually. So that is what this is. This is Amazon product CSV. This is final product list. So it is very big. We cannot open directly in this CSV. So that's why I'm unable to show you in the Excel. So you can see it here actually. This is what is the main objective of this phase one. So just cleaning and generating a new all product data set. That's what we did here. And next we move to phase two. So this is where it's the main crux of this project will step in. So here we are just loading some libraries, you know, these pandas, and here we are loading two important libraries and functions actually. The first one is sentence transformers and this FAISS. Okay, so sentence transformer is used to embed each row of this CSV file into a numeric vector format. So we have a total of 1103197 products, right? So each product represents one row, and we have 384 columns actually. So if you look at here, we have just 6 columns here, and if you look at here, it is saying we have 384 columns. That is the main thing actually. So what does this represent is, if you go to my earlier tutorial code, this is my earlier tutorial code. What we do is, if you take any sentence, for example, the warranty period of this product is 12 months from the date of purchase. This is our actual words, right? So we embed this natural language text into something like this, a numerical vector format, and the length of this vector can be 384, 768, or 1536 depending upon the model. So here we have different models. So each model generates certain length of vector space actually. So here OpenAI models generates 1536 3072 depending upon the small or large models, and we have 384 SBUT model, and we have BG small 384, and we have actually depending upon the model we get the vector dimensions. Okay, so in our model we have choose all mini LM L6 V2 model. So that is this model. This will convert any given text into 384 element vector. Okay, so that is what it is representing here. So whatever the title, this text clean, we have it, right, that we developed in this previous phase. So we have taken that and we have converted this text clean into a 384 numerical vector. Okay, and then after we converting each of the row into its corresponding numerical vector, so what we do is we generate all those things into a FAISS index, because FAISS index allows you to do the similarity checks actually using cosine similarity or some other similarity techniques. So you can match the similarity of the query and the products. After we develop the entire FAISS index, we will store that entire FAISS index in this file product underscore index dot FAISS. That you can see it here actually. Along with this index, we also save this embeddings what this embeddings for metadata. So what this represent is, so here we are just exporting only this text clean into this numerical vector format, and remaining all these things, title, price, we are not touching those things actually, because we have all those things here in this text clean column. So why we need that metadata is, for example, if the product find out some rows are relevant. So if you look at the index, all you see are numbers, a numerical vector 384 column size numbers actually. So based on the location of that row in the FAISS index, we will just compare with the metadata and we will find the relevant corresponding product for that corresponding row actually. So that is what we are doing. And once we save this FAISS index and metadata files, so all we are doing next is to build this semantic search engine products. So here we thought of building three different types of search engines. So the first is basic semantic retrieval search engine actually. So here our objective is simple. So whenever you give a query, it has to pick all the relevant products in the index and give you in the way that you can understand. If the model gives you just a number, a numerical vector, we cannot understand anything from that numbers, right? So we have to get the data in a human readable format. So that is what we get from the metadata file actually. Once we get the FAISS index numbers, we get compare those FAISS index numbers with the metadata column numbers, and then we get the retrieved products. So that's what we are doing here. So this is what basic search function looks like actually. So what we do is we will perform a basic FAISS based semantic search over the product metadata. So we just take the query, and the top k means how many results we are expecting. So that is also we are passing into this function. Once we pass, we get the query vec in a numerical format, and then we compare with the index for similarity. And once we get the distances means the similarity score between the query and the product results. So we will sort them, and then we will take the top 10 closely relevant products actually, and then we will pass those results from this search engine. That is what this basic thing doing actually. When we type affordable running shoes for men with good grip with this search function, and we pass this query and top k, here we are expecting some 5 results only. So that's fine. Even if you do not mention anything, that is also fine, because we just take the default value as 10. Okay, we get some results and we print it here in this format actually. So these are the products that we got. So when we type affordable running shoes, we have got 5 matching results: running shoes for men, lightweight, life running shoes for men, Wanders running shoes, and Oxy running shoes for men, running shoes for men. So we have got 5 things. So at this stage we are performing some verification checks on this results actually, whether these results are coming from the product list or somewhere this garbage results actually. I just want to confirm these things. So that is what I'm doing here actually. First one is inspecting by the product ID. So here we have this product ID, right? So I'm taking this product ID and I'm just comparing this product ID in the metadata list actually. So that's what we're doing here. So product 492072 is Adoxy running shoes. So if you look at here 492072, this is an Adoxy running shoes result. So overall our search results are great. They are accurate in the sense they are, we don't know whether they are relevant to the query that was asked, but one thing that we can confirm at this stage is these search results are from the database that we passed to this. And the next verification method is cosine similarity actually. So this is the very fundamental similarity check that we are performing actually. Whenever we send a query, we convert that query into a numerical vector, and then we take that vector and we take the vectors of all the products that we have in our database, and we compare the query with each product in the index actually. So when we are comparing, we are expecting some similarity score from each product actually. So this similarity score is evaluated using cosine similarity technique. So basically it returns values between -1 and 1. So a score near to 1 means very similar. A score near to 0 means very completely unrelated, and a score near to -1 means completely opposite. So this is a garbage actually. In most of the cases, we expect values of similarity score in these ranges actually. So here I have written what makes a strong match. So a value between 0.8 to 1 is a very strong match. 0.6 to 0.79 is good semantic similarity. Zero point 0.4 to 0.59 is a weak or vague similarity. Less than zero point 0.4 are likely irrelevant. So these are the scores that was generally accepted in the literature. If we take a similarity score, we have got 0.73. So that was a very accurate match. Here, if you look at here, so the cosine similarity that we get is 0.73, and if you look at here, the score that we have got is 0.49, and here in the main product that we are verifying, it is 0.53 actually. So here 0.53 and here 0.73. So these are different. So this is cosine similarity, and this score is not a cosine similarity. This is the Euclidean distance between the query and the product. These two are two different things. So in order to evaluate the cosine similarity, we have to do some more calculation that I did here, but I didn't do it here. So if you want, you can add that cosine similarity logic here. And next, in the next phase, so here in this phase, we have got all the products, right? So here there are some drawbacks actually. So in this list, there are many products that are repeated, and the another thing is these are not sorted, etc. So it just dumps the results that were retrieved from the database actually. So if you ask it for 10 results, it will just give you the 10 results, even if there are some duplicates inside of it actually. So it doesn't care about it. So that's what we are doing here actually. In phase 3.5, we are adding some additional logics. After we get the results, we are removing the duplicates, and then we are sorting the results based on the price. These two additional logics that we are applying and generating a new list of products actually. Once we are done with this code, I'm just saving this notebook into a .py file like this. Why? Because so we are going to load this py file in Streamlit app. And after we done with these two basic searches, in the next one, we are starting out for developing this LLM based search engine actually. So what we need to do is, so first you have to get your OpenAI API key, and then you have to store it either in your bash rc JSH profile or dot profile if you are in Windows. So you have to store that in your environmental variables list, and then use your .env to load it into this current file. After we load it, so we are just loading out the same transformer, sentence transformer that we used to embed the product list. So here we use the same model to embed the user query also. So here we are just loading out the metadata and FAISS index. So we are just taking the products function that we have developed here actually. So we are not going to do anything special here. Think of it as an extension to this phase 3.5. So in phase 3.5, we have filtered out some duplicates and some sorted out by price, etc. We have applied some additional extra logics to clean up the results actually. But even though we got some decent results, we can further filter out them. We can evaluate further relevancy checks using this LLM that we are doing actually here. Okay, so based on the results that we have got, we are just passing them to the LLM as context in the prompt actually. Here we are developing that context. So once we have developed that context, so we are generating the prompt here actually. So this is the overall prompt. You are an e-commerce assistant. You must strictly follow the product data provided. You are not allowed to invent or modify product titles, prices, categories, or links, etc. So here is the query that we are passing, and here is the context that we are passing here actually, that we got it from here. Okay, that's the context, and then here we got the context from this function, and then after we got it, so now return 3 to 5 of the most relevant products in this exact format. Do not summarize, do not guess, do not reword. So we want exact product list to be printed actually. Okay, here for debugging verification, just to understand what kind of prompt that we are sending to the LLM. So I'm just printing out here. So in this we are using this GPT 3.5 Turbo, and here I'm setting the temperature to 0, meaning no creativity. So here I'm applying some parsing logic, meaning we want the results to be printed in this way, right? So we have some emojis for each line actually. So That's what I'm doing here. In LLM, we get the results in a paragraph or a dump format. We are just formatting here, okay? And this is the total prompt that we send to the LLM. So overall, 5 products that we send, and we got these products actually from the LLM. So LLM thought these are the best products out of the list that was generated in section 3.5. Of those, how many products? 1, 2, 3, 4, 5. So these are the 3 products that are best. You can verify this thing actually, whether the product that were generated by the LLM are not hallucinated. Okay, so I have just taken one example, 490679, and we have got the product details here. So these products are available in the product database actually that we supplied to the LLM. Here in our earlier phases, so here you no need to verify these results actually, because we have given the data and we are not making any LLM based things in these two first search engines actually. So there is no chance for hallucination. But with LLM, it is very different. Even though we supply an exact data set, LLM will hallucinate and invent things actually. Sometimes it make things very complicated. It shows up its creativity. So to avoid this, so I'm just verifying whether the product is available in the product list or not. And in the end, after we are done with it, I'm just saving this file also to .py file to use it in our Streamlit function. So here, if you go to one level above, so here you see this app directory, right? Within that, I have written this streamlit.py file. Here in this streamlit app.py, so I'm just loading the 2 files that we have developed in P3. So here I'm loading one, and here I'm loading the other, the second py file for underscore llm answer underscore gen. These are the basic functions that I'm loading from these files, such basic and such products, and from LLM file I'm just loading the same such products. So basically this such product and this such product are same, but I have copied them into different files. I'm just loading each from the relevant file actually. I'm just loading the such products as LLM such products, and this file and this file actually. Here I have given the syntax for the Streamlit app. So this one is the title that you see here, and I'm just closing these 2 links, and this one is the search button, and in between you have this slider. So that is what we are given here. This is the slider, and then I'm doing some basic results filtered, and this results from LLM, and then I'm printing them in this data frame format actually. So here like this tabular format. So this is the overall code for this Streamlit app. So you can run it. You can run it using this Streamlit run the file name.py. So I have given these instructions about how to run this app, etc. in the readme file. So you can find that readme file in this directory actually. So this is the overall project structure, and then I have given all the instructions that you need to do to finally generate this kind of web page. Okay, and here I have provided this requirements.txt. So you just have to run this requirements.txt like pip install -r requirements.txt. If you run that pip install -r requirements.txt, so all these libraries will get installed into your machine environment. Okay, try to install all these things in a separate environment. Once you run these things, so you have got this kind of results. So for example, you can try out another search like best mixer grinder. If I increase the product list to some say 15, it is running all the phases. All the phases means we have phase 1 2 3 4 and 1 2 3 4, right? So basically 1 and 2 it won't run. Phases means it will evaluate the search products basic search, and it will evaluate phase 3.5 results, and it will evaluate phase 4 results and returns here. So here it returned Preeti steel max mixer grinder, and another mixer grinder for chutney, etc. So here we have given 15 products, and we have got them all. So total 0 to 15. Okay, but there may be some duplicates. So for example, if you look at here, mixer grinder 3 and mixer grinder 4, they look same for me. Not sure where is the difference. So here is 14762, here it is 14762, meaning these two products are same duplicates. So in the next list, if you go to here, what is that? It is mixer grinder chutney. It is mixer grinder chutney. Here this one 14762, it just deleted the duplicate and sorted the results in the ascending order. Okay, that's what we did it here. And after deleting the duplicates, so our products finally became 12 products, 0 to 11, so 12 products. So here in the first list we have got 15 products, and in the second list we have just got 12 products, meaning 3 duplicates were deleted. That's what is happened here. And in the end, phase 4 results, so we have just got 3 because we asked just 3, right? So of these things, so LLM thought like these are the best products in the above results. So these are direct searches from the FAISS index, but these are direct searches, but along with that, we apply some LLM model techniques. Like actually in the clean title, for example, we have this product ID text clean, right? This is what we are encoding into the FAISS index, right? Within that, we have details like ratings, okay, category, and the product title, etc. are available actually. So it will understand all those things and make sense what is the best product. So that is what happened here actually. So here we have got the basic list, and here we have deleted these duplicates and sorted the results. But in each of this text clean, we also have ratings and the total ratings and the number of ratings that were given to each product. We have those details here actually, but those were not considered in this first two. Okay, those were considered here in this phase 4 actually. So that's what overall is happening in all these three semantic search engines. So that's all about this tutorial. If you have any questions, please feel free to ask in the comment section. So if you like our video tutorial, please subscribe to our channel. See you in the next tutorial. Thank you. Happy learning.